My name is Jaeheon, and this is my colleague JC. We're from Google, and today we're going to talk about ThreadSanitizer and heap sampling. Click. Try again. So basic outline is intro, ThreadSanitizer, heap sampling. We'll conclude. It's very simple. So as programs get more complex, there's a lot of questions people ask about what's going on in their program, especially when things go wrong. So we're going to talk about two tools today. One is ThreadSanitizer, which finds data races for you, and one is heap sampling, which tells you what is being allocated when you run your program in production. Okay, so first, ThreadSanitizer. So all of you in this audience know very well what a data race is. You've found them, you've caught them, you've fixed them. But to illustrate what the tool does, let me just walk you through a very, very basic data race. So here's a Java class C. It has a static int field called x. There's a setter and a getter. There's complete absence of synchronization. So when you compile and run this program, you may see a trace that looks like this. There's two threads, T0, T1. T0 enters the set method, writes x, exits. T1 enters the get method, reads x, exits. Very simple stuff. And what the tool does is tell you that, you have a race on x. And that's very binary. It's not really interesting. So it actually gives you a lot more. This is a sort of stack trace type race report that you will see. And it's a lot of text, but it's worth going over a little bit the contents. So at the very top, you can see that it's the ThreadSanitizer tool that's telling you there's a data race in this program, 7616. There's 4 bytes being read out of some machine address by thread 26. And the place it was read was c.get on line 7, which was called by a.get on line 6 of a.java. A little below, you see a C function that was calling this Java function. And below that, you see a J and I stub. So you can see that the thread has been wandering through various languages. And it's the same thing for the right. So the rest of the talk is to kind of explain what goes on between here and how do we get to here. So to explain what's going on, I do have to talk a little bit about happens before. We already saw what happens before is yesterday with John Rose's talk, but let me just set the stage a little bit here. So let's say we have this trace, just like we saw before. And the question that we really want to answer is, does the write of x by t0 happen before the read of x by t1? So this is the question we're going to keep coming back to as we progress through the slides. So here's a very condensed, simplified definition of happens before. First, we take what I might call the thread event order. It's very intuitive. So in T0, enter of set happens before the write of x, and write of x happens before the exit of set. Very simple. In T1, the same thing. Enter of get happens before read of x, happens before exit of get. The second part of the definition has to do with synchronization. So let's pretend that the set and the get method was properly synchronized with, say, a class lock. So the trace might look something like this. Around every access, there is an acquire-release pair. So this thing is properly synchronized, and now I can bring up the release-acquire order, where the release operation of a particular lock happens before a subsequent acquire of that lock. And finally, to bring it all together, you bring in transitivity, and now we can talk about the famous cones of causality, where all the events that are known to T0 up until that release happen before all the events that follow in T1 that occur after that acquire. So that's all good. Now, since the write of x happens before the release, happens before the acquire, happens before the read, transitivity tells us that, yes, write of x happens before the read of x. And so we may legitimately conclude that there is no data race on x. So going back to our original trace, the racy trace, we can examine the happens before relation. And we say, yes, there is tons of thread and event ordering, but there's no release acquire order. And no matter how much transitivity you add, you're not going to get from write of x to read of x. So there is no happens before relation. And so we may conclude that there is actually a race on x. The thing to note here, though, is that happens before is a mathematical relation. If you fire up GDB and examine your program, you're not going to find the happens before relation in your program. It's in our heads. So to actually do this analysis, what you actually need to do is track it in some fashion, and the way we do it is with something called vector clocks. And in some ways, a vector clock is kind of self-explanatory. It's an array of logical clocks. It's an actual data structure. But the way we use it is particular, and we have to interpret it correctly. So instead of going through the algorithm as per definition, I'll just walk you through an example. So let's say, by way of example, T0 happens to have a vector clock, 4, 0, at the time after the acquire of that lock. So the way to interpret this is the indices in that vector clock all are for each thread in the system. So if there's 100 threads, this vector clock will be 100 long. It's for T0, so if you index into 0, you see the number 4, and that is the current time for thread T0. All the other indices, all the other values in that vector clock indicate the last time at which another thread had synchronized with this thread. So next thing to do is we do a write, and when we do a write, we simply remember what the timestamp was. So we just record it off to the side. We advance, we actually do the write, and now we come to a release. And when we do a release, we do the same thing. We kind of remember, the vector clock when we did a release for a C.class was 4, 0. The interesting thing here is, according to the algorithm, we will increment the current clock from 4 to 5, and then life goes on for this thread. Meanwhile, for T1, by way of example, let's say that the current vector clock for T1 was 0, 8. So it's thread T1, and when you index into 1, the current time is 8. And 0 on the other clock means we haven't synchronized with T0. When we do an acquire, this is the way we do the acquire update. We take the current vector clock, we take the last vector clock seen for that particular lock, and we do a pairwise update throughout the vector. So for the first entry, 0 and 4, we take the maximum 4. For the second one, it's 8 and 0, so we take the maximum. So the vector clock gets updated to 4, 8 for T1. We do a read, and just like before, we remember what the vector clock was when we did that read. And life goes on for this thread. But now we're ready to do a particular check. We say, OK, the question of does the write of x happen before the read of x gets translated to this equivalent problem of is the write of x vector clock pairwise less than or equal to the read of x vector clock. So we take the two vector clocks that we've seen before, and we do a pairwise comparison. And we say, is 4 less equal to 4? Yes. Is 0 less equal to 8? Yes. The answer is yes. And this pair of axes do not race. So now it's very simple to go to the first example, the racy example. We start with the same vector clock, 4, 0. We remember it. We continue. In thread T1, we have the same vector clock, 0, 8. We do a read. We remember it. And we're ready to do that check. So the check is the write of vector clock pairwise less equal to the read vector clock? And here the answer is no, because 4 is not less equal to 0. So because of that, we can say that there is a data race on X. So this is the happens before approach to data race detection. And it's the primary benefit is that there are no false positives. And what I mean by that is when this tool generates or issues a race report for you, you can be assured that it is a real data race. So developers like this sort of property. Yes, they do. The catch is that there is some work that we have to do. That is, we have to instrument every synchronization operation that goes on in the system. If we happen to not see the acquire release pair, then we will falsely report a race. So that's something to keep in mind. And all this is not new. This has been ongoing research for the past 30 years. And a lot of work has been done to do performance optimizations for the vector clock algorithms to minimize the amount of updates and versions and whatnot you have to do. And also, there's a lot of work that went on to have a rigorous mathematical proof that whatever vector clock algorithm you invent, that it actually corresponds to the happens-proof relationship in a tight way. All right, here's references, standard references you can go read if you want to learn more. So we didn't go out and reinvent or re-implement vector clocks. Instead, we took vector clocks that were already implemented by ThreadSanitizer. And this is a C++ data race detector from the LLVM project. It's fast, it's optimized, it's maintained. And in its typical usage, what you do is you take your native code and you compile it with TSAN mode turned on. And it will embed hooks into your object code. And then when you link your native code into a final executable, the TSAN runtime engine comes along with it. When you run the program, in the background, there's vector clocks being generated and merged and updated and checked. And on a bad check, that's when the tool will issue a data race report. So that's how we use it. For our purposes, we need to ensure that the ThreadSanitizer engine and the JDK play well together. And this has not been an easy process because both are complex runtimes that each try to assume ownership of the process resources, which I won't go into here, but you can ask me later. The basic, though, is that, that TSAN provides C hooks that are conceptually very simple. And what we do is we embed those C hooks into various places in the interpreter and the JIT. So some may ask why we haven't pursued bytecode rewriting, and basically the answer is native code. So at Google, every Java program pretty much standard comes with tons and tons of native code, and both the bytecode and the native code, the Java code and the native code keep evolving very quickly, so there's never like a stable point where it's like really safe. So it's important for developers to be able to catch data races in both the Java side and the native side. Because of the no false positive guarantee that we want to provide, we do have to see all the synchronization, and that means not only Java locks, but also the native locks, and also the JDK locks, and et cetera. And it is the case that in some programs, Java data is protected by native locks, and vice versa. Sometimes Java data is protected by native data is protected by Java locks, and Java data is protected by native locks. It's not common, but it does happen, and if you have a bytecode rewriting approach, you are not going to see that all. And because it is the reality that a lot of Java threads will wander through Java and JNI and native and all that, we do want to see the full stack trace for usability purposes. And we believe that having an embedded approach gives us more performance headroom to work with later when we do want to like actually tune this tool for performance reasons. Okay, so kind of the basic approach is you want to tell TSAN everything. And let's start with how TSAN manages metadata, like the vector clocks and whatnot. The basic approach for TSAN internally is when you allocate a C object or a C++ object, you have the pointer, and that pointer is literally the key at which you can access its metadata for efficiency. Now, since we have internal access to the representation of a Java object, the OOP is a natural fit to give TSAN a track. So life seems good, but then objects move around, and this is problematic because TSAN typically doesn't really deal with C++ objects that kind of ephemerally move around. So what do? We tell TSAN about the object lifecycle. So on a new, we tell it, oh, here's a new object. When it gets collected, we say, okay, don't worry about this object anymore. And in particular, when GC happens, we tell TSAN that, hey, this object moved from place A to place B. It's an implementation note that we don't instrument the GC itself for performance reasons. We don't want to touch the hot paths in the GC, but we can pretty much accomplish this in a post-GC phase. Synchronization, so we take these two callbacks called TSAN Java Acquire and TSAN Java Release, and you just pepper them throughout the interpreter in the appropriate places. And it happens that there's a lot of subsystems to go cover. So there is the object synchronizer, there's the volatiles, there is the places in interpreter and JIT, there is a Java util concurrent, there's JVM and TSAN locks. It goes on and on. So you want to have a good coverage of all the synchronization. And finally, the reason we're doing all this is because we want to track fields. So TSAN read and TSAN write approximately are the right callbacks to use here. And most fields get instrumented, except we want to cut out instrumentation when we can. So volatiles, for example, have synchronization semantics, so they will never race in a technical sense. So we don't bother tracking whether volatiles race or not. We do keep track of their synchronization. Similarly, final fields never race, so we just skip those. And for special lazy initialization idioms used, the tool can't really understand it that well, so instead we go annotate those in the source code, and those annotations are tracked, and we make sure to not track certain fields. So I said let's tell TSAN everything, but you don't want to tell them like everything. We want to tell it like almost everything. And the things we don't want to tell TSAN are things like what's going on in the VM itself. So in particular, we don't take libjvm.so and compile it with TSAN instrumentation. And what we don't do is we don't make the save points or the internal VM utexts visible to TSAN either. And the reason is, if we did that, it would expose a lot of internal synchronization that is not visible or usable to user code. And what happens is there is a lot of parasitic synchronization that gets tracked by happens before, or tracked by the tool, and suddenly you're not going to see a lot of races. Finalizers tend to be annoying, and we decide to ignore those for now. And the precise behavior of final field references turn out to be quite tricky to track properly, so we cheat a little and tell TSAN that those are volatiles. And it's actually too strong. It introduces too many happens before edges, but it's good enough for now. So that all gets us to the place of, okay, here's a data race, and now we can kind of talk about, okay, how do we get this stack report? In particular, how do we get the top 2 stack reports, for example, the top 2 frames? So the basic approach is, what TSAN does is, for native code, it's going to take program counters as 8-byte tokens and maintain what they call a shadow stack. So upon function call and entry, or entry and exit, the 2 callbacks are TSAN enter and exit, and you feed it the program counter of where you came from. For memory access, you just remember which particular program counter that you're doing that read or write. But Java doesn't really have a program counter per se. So for Java, what we've done is take the JMethod ID and the bytecode index and smash them into an 8-byte token and give that to TSAN to use. And that turns out to be a pretty good compromise. So this is what TSAN does most of the time. It's just recording and recording and recording. It's just remembering a lot of little program counter tokens to remember where it was. Now, when it comes time to generate a report, there's a real data race, then what it does is extract the shadow stack and start symbolizing each program counter in each frame. When it sees a Java program counter, it asks the JVM to please turn this into a C string. And because races can happen at arbitrary times, we have to be able to regurgitate or symbolize these tokens on demand. So we can't wait till like the VM is at a nice place or anything. So to put this all together, again, we have this racy trace. If we kind of look at the hooks that are in play here, you may see something like TSAN enter and exit. The write was instrumented with the TSAN write function. And the curly braces indicate a JMethod ID and a bytecode index pair. So this is something like what you might see. And the operations TSAN does to get you that stack trace will look something like this, where when we do the read and it say, okay, there's a race on X, it first queries the shadow stack and says, okay, the top of the stack is m,5, and the next thing is k,4. Then it says, okay, please symbolize m,5, and the function goes and queries internally in the JVM what the nice C string is, and it'll say something like c.get at line 7, and k.4 will do the same thing. We'll go ask the JVM. For non-Java program counters, you simply, it has its own internal routine to symbolize. So the impact of this tool across Google has been that it's in use by various teams across Google. The typical way one uses it is you take a particular VM flag and you stick it in your automated test config. And upon continuous build and test, it'll exercise this, this configuration. It is the case that the native-only mode for ThreadSanitizer is still the most widely used one. That is, we don't turn on Java field tracking as the default. And that is due to 10, 15 years of Java development without a tool to catch these races. So it's pending a depot cleanup so that we can just turn this on by default. When you use this tool, it forces cleanup of dodgy code, as one might expect. But this has turned out to be a slow process, even for our own team, where we do understand these things very deeply. On the other hand, it has forced a lot of fixes in third-party code, so that's a side benefit. And the other interesting phenomena is that running this tool, we've seen a steady stream of data races exposed that are internal to the JDK. And typically, though, when we go ask the experts, they say, yeah, that's benign, don't worry about it. So typically what we do is we suppress them. Because the reason we're doing this tool is because users want to figure out what the data races are in their own code, not necessarily what all the races are in the JDK itself. So ongoing and future work, we have the interpreter all working. C1 is in progress, and typically our concerns are, is it correct, and is it usable, and then we'll chase performance. As I had alluded to, final fields and finalizers aren't really going to be, we haven't quite dealt with those yet, so that's perhaps future work. JDK 9 is coming, and so there's a forward port in my future, and we'd like to perhaps think about upstreaming this one day so that it's a big patch, so we don't really want to have to carry it forever. Okay, so that was my talk, and I will now hand it over to JC.
Thank you. So I get to press next. So once you've actually played with ThreadSanitizer and you made your code totally thread safe and with no other problems, a common question becomes, what is actually being allocated by the heap? And often I find that when you try to understand heap in general, you'll start having questions of quantitative. How much heap am I using? At some point, you're going to go, well, this is either OK or not. And when it's not OK, you're tending to go, OK, wait, what is allocating what kind of objects, how many, et cetera. And the reason we started this was basically we wanted to understand memory usage using sampling to have a very low overhead. And my part of the talk is kind of like a mix between going down memory lane of 10 years at Google with an implementation that's a decade old, and the work of actually upstreaming this with a JEP in open with a serviceability dev email thread that's pretty long by now. So I'll go through that. And so basically the main features of what we want is a very low overhead, 1% or 2%. The reason we want that is that we like having this on by default all the time. And so people can actually go and figure out straight away what is being allocated, what has been garbage collected types of objects at runtime with no cost. And we want to be able to pull that directly. And the information that we provide to the users is accurate stack traces, so of the objects, their sizes, how many of those samples of those objects did we see, which ones are live, which ones are garbage. And I'll go through that as I talk. So I always do a couple of preambles of presentations so that people know what to expect. I don't have any benchmark numbers yet of this internally. We know it's 1%, 2%. I'm going to be working in the near future of getting numbers on the serviceability dev thread so that people can see what to expect. We don't expect anything else than 1%, 2%, so that's what we see internally, but still. If you do want more numbers, if you want to know it now, just contact me. I'm currently on paternity leave officially, but send me an email and I'll handle it when I come back. Second one that I do, and I hesitated putting this one, but I thought it could be an elephant in the room. What about a JFR event? There are JFR events that handle like TLAB full events that would tell you this is the object that was allocated, but TLAB was full. The thing is that we like having a means that a user can say, I want to know every megabyte in average. And that average is the important concept because we don't want it to be an exact megabyte. Because if you have a recurring pattern of allocations, you'd always hit the same object in that pattern. We want it to be moving around that megabyte area so that you can actually really sample correctly the different objects. And we don't want to be defined by whatever TLAB is doing for its sizing. We want to preserve the stack traces for garbage collected objects. We want you to be able to say, hey, what has been garbage collected? What are the objects that are being churned by my system? And we wanted to have an ad hoc way of being able to get those sample objects. So, and the third one is, like I said, there's a JEP for this. And so you can look at the JEP. There's an ongoing email thread, which is becoming long since it started the story with the internal implementation and now has morphed to where we're going towards getting it in. And I'm aiming for JDK 10 and working with Oracle to get into JDK 10. And we'll see how that goes. So the information in these slides is either details of what we have internally or what we're currently suggesting as for the JEP and web revs. And please stop me if you have questions at any time during this presentation. So hopefully this is not too small, but I wanted to get all the API up in one go. It's handled by JVM TI. It basically has a way that you can programmatically say, start my heap sampler. What is the monitoring rate? So do you want every megabyte? Do you want every 512K? Do you want more or less whatever? What's the max storage? I'll come to that in a minute, but basically it's the fact of how many garbage collected objects do you really want to keep. As the live objects, you basically are adding a tag and a little bit of information to each live object, so you're not going to be adding too much memory to the heap. But if you started trying to remember every garbage collected object from the start of your program, well, if you're churning a lot of objects, that could become quite big. And so we have a max storage there. You have a stop, which is just a stop. The stop actually, for the little details, will remember what was allocated and what died so that you can actually pull it afterwards. And then you've got your 3 getters. Get your live objects that are sampled, get the garbage ones that are currently recently garbage, get the frequent ones, and so that uses a tiny little algorithm to remember object allocations in a way that it will actually show you what were the frequent ones. And then you've got release to be able to release whatever was allocated by the get live, get garbage, get frequent. And the last one that I've added is statistics of how often do we sample, what are the object sizes that we've sampled, things like that, which allow you to double check what is going on and allows me to easily debug what's going on. At Google, basically we have 512K as a default for the monitoring rate, and our GC objects is set to 200. So we remember the 200 last garbage collected objects, and that generally has been enough to figure out what's going on. From a data structure point of view, we created for this web rev a new JVM stack traces, and then basically it has a stack trace array, which becomes a JVM TI stack trace, which we created also, and this one uses JVM TI frame info, which already existed, right? And that basic system is the method ID and the location in the method, and that's all you need afterwards. Now, what does this really mean for the user that uses this currently? Is that basically you have the basic information, but as a user of this, you still have to decode this because you only have the method ID and your location. There is actually an implementation in GTReg, the testing system I put, that will decode this and make it into a nice text format. I currently don't know if this will remain in GTReg only. Will we make an open source library that will use this? I have to start talking and figuring out what would be better. So, as a sampling overview, really what happens is when you do heap sampling, right? Basically what you've got is you've got a nice Java job which creates a nice little object, and at some point, and I say at some point because I have 2 implementations, I have the Google one that we have and the one that we're working on in JEP, and I'll show the differences. You're going to hit a threshold and you're going to say, well, I want to sample now. I actually want to remember this. And so you'll collect your stack trace, you'll get the object information about it, and then at some point what you're going to do is you're going to want to store it somewhere. And the storage, you're going to give an API like I just showed you. And that API will be available for debugging, profiling, monitoring, right? The logical things. And those items, the way we do it with JVM TI is we provide it to your user and Java job directly, and the user Java job can use that to actually retrieve and request that data, right? So then your Java job can automatically provide this to, as a server, for example, to whatever users that want to see it. So, as an example of really what you've got, it looks like all the other stack traces that I've seen today. You basically, if you wanted to look at live objects with stack traces, you'd have a number that tells you what is the accumulated size of those objects that I've seen, right? So you have an idea of how important this stack trace really is. It also gives you the number of samples that have been seen, right? Which gives you also the frequency that you've seen it. And then it gives you evidently the frames, the method line, and the number in the file. right? The only difference that we have here compared to what we have internally is internally we do what Jaeheon was talking about is we provide native frames also. And here currently in my version that's in the upstream WebRev, we only have the Java frames. And the differences are because we don't use async get call trace. We used vframe walker, right? So what do you have for garbage? Like I said, garbage provides you information about object turning. It'll provide you what is the frequent garbage collection that has been allocated. Recent really is the last 200, for example, if I have 200 as my number. And frequent has a way of filling up that buffer and then less and less updating it. So that really what happens is you need a lot of objects to be sampled before you get a new entry in it, which will have an effect of that array is going to remain the most and more identical throughout time, and you need a lot of objects to update it. So you really will get at the end what was the most frequent. And so once we have those, I gave you a text format, but internally what we've got is we provide a protobuf, and then we provide it to other tools afterwards, which is easy to pass around. Or we have that text format that is really easy for debugging. And that's basically my view of this for the JVM TI API was to keep it bare bone and then just let the user build up whatever they want on the other side. So like I've been saying, we've got two versions, and I'm going to have the next couple of slides to just show you the differences between the initial version used compiler changes, and so there was modifications to the interpreter, C1 and C2, to handle the sampling. And the second version comes from a conversation of 2 years ago between Jerry Manson from Google and Tony Penensi? Thank you. From Twitter. See, I looked at the name this morning, but anyway. And he was advocating for piggybacking on the TLAB system. And I'll explain how it works to piggyback on the TLAB system to make this work. And so that is the current one that I'm testing in the WebRev upstream. And so basically, oversimplifying at a JVM language summit, right? So don't kill me. You've got Java bytecode, you got an interpreter, you got C1, C2, and the internal version basically changed, added a little bit of code to your interpreter, to your C1, to your C2, and basically all this code would always say the same thing, which is how many bytes do I have left till next sample? And they would all use the same thread local amount to be able to say, okay, please sample this. And that code would just jump into collect the data, which would be common code between the three. And at that point, you'd have the internal storage, which handles what we showed in a couple slides ago. So the disadvantages, because I like starting with disadvantages, code generation now becomes complex. You have to change interpreter C1, C2. You're adding code to code generation, which means you might be changing the way optimizations are handling it down the line. And you have to handle each compiler tier. There are advantages, though, to this, which are you can easily turn off one tier if you want. You don't have to have it on for all. And the code is directly handling the bytes left subtraction. And I'll show why in TLAB it's a little bit more tricky. Right? So those are the advantages to this. However, one good advantage with a TLAB is that basically they all share relatively a TLAB version. There's fast TLAB refill, which is a side story, which I'll keep aside. Ask me questions if you want. And it all falls down into, at some point, a common code that says, well, is TLAB full? Yes. And if the TLAB is full, please get me a new TLAB. And at that moment, we can add our own code in a single spot in hotspot and say, okay, please double check. Actually, is this a real TLAB end, or am I wanting the sample? And how you do that internally is a TLAB has a start point and an end point. If the end point is 2 megabytes down the road, but I just want to see what the sample would be in a megabyte, I cheat the system and tell it that the end is actually a megabyte away. And when I come back to that point into here, I say, oh, wait, actually, I tricked you. Actually, let me put back the TLAB end to where it wants to be. Now I know I want to sample this. And so I'm using the exact same code generation system. I've just cheated pointers and bumped pointers around. And so the implementation is quite simple. And again, you can see it's in WebRev available to all. So then what happens is you fall back into collect data and you fall back into internal storage, and that code is exactly the same regardless of where you came from. The disadvantages of this is that, well, TLAB has to be on, otherwise you don't get it. And you do add complexity to TLAB implementation because now, so historically, the Eden space pointers is, the TLAB implementation is piggybacking on the Eden storage pointers, and now we're piggybacking on the TLAB pointers to say, oh wait, we want to sample. So we got like a bunch of things here that are happening at the same time that could go wrong. So it's a little bit hairy. Advantages though, very little common code has changed. It's currently at least architecturally independent. There's no changes to the architecture code, and it can be turned off and on at the flip of a switch, and you don't have to recompile things. In the compiler world, if you've got a C2 compiled code that is using the sampler and you no longer want to have the sampler, you have to recompile it. Here you don't. So that's the advantages. Internal implementation details, just because. All sample-live objects are actually in the list. What they do is the list gets traversed at GC events to keep pointers up to date. Dead objects get sent, like I said, to a round-robin array. And then the user can define that size of the array. The next sample is not always X kilobyte, like I said. If you want to be able to hit meaningful data, you don't want to hit every exact 512K, for example. You want to hit around it so that if you have a pattern allocation, you hit all those elements. And so that's why you do that. Where is the WebRev up to? A lot of the code is done. Initially, I had dumped a simplified version of what we had internally to Google. I had put out a couple of things, and then I started adding to it. And then we moved to the TLAB implementation, and so now we can compare both if we wanted to. There's a lot of testing going on. I've added a lot of JTReg tests so you can actually see how it would be used, and there are a bunch of variations of what you would want so you can actually play with it and you see directly examples. So I don't show a demo here, but you have it directly in the JTReg folders. And we have internally a version that handles multi-threading, because evidently if you have multiple objects that are hitting your common storage, that sounds like a bad idea if you're trying to do it without any protections, then ThreadSanitizer would yell at you. And so, but for simplicity right now, that's out of the WebRev and going to be added as a future item as we move forward. And handling native frames is something that we like to have. So future potential items, and I put future potential because I don't want to force myself in a corner, and I don't want to force people to have to accept things in a corner or whatever. So the potential is there to keep me safe. It's handling more stacks such as the natives and make sure that we actually get those because they're important. Keeping track of additional information. So you have the fact that this object is alive, but you don't know how long ago it was. And there has been requests, at least internally, of like figuring out how many GC cycles it's actually survived. And since we go through that list anyway, it's kind of easy to bump an integer up every time. And then add user context information. It's a feature we have, which is to allow you to say, well, I'm at this point and that point. I would love to know the sample objects of this part of the code. So could you just filter out what I don't care about right now? And so that's something that's practical and not too difficult to add in. There's also a callback sampling system. So if you actually want to get a callback at that moment of the sampler to do something, it's something that's tricky to do because at that callback, you're not allowed to do a bunch of things. Jeremy knows way more than I do on this one, but I know that I think you're not allowed to do JNI calls and things like that into those callbacks. So there are things that, would you allow that to happen or not and let the user take that risk or not is a conversation to be had. And then, like I said, provide a user library to generalize deciphering, because as it is, if a user wants to use this JVM TI as is, you basically get an array of integers and longs, and that's not really practical. So you probably want to straight away say, well, if you want to use this JVM TI API, here's actually a nice friendly user API on top. And so that's something we have to work on. So I don't know how fast I went. I apologize. I had not prepared a dry run on this. Low overhead solution to understand memory allocations is really what this was about. We really want to provide a meaningful way of knowing what has been allocated, how much it's been allocated, and be able to provide that as a user when they want to try to reduce your heap usage. Knowing the object counts and the stacks have been really the most important parts of this, and knowing exactly like an accurate stack. Where to find information, like I said, you have a general presentation of it in a JEP here, and then there's an ongoing email thread on the serviceability not dev serviceability, mailing list that you can find. It's long conversation now, but jump in. So as a real general conclusion, I suppose, what we try to show, Jaeheon and myself here, is that we work on tools such as ThreadSanitizer that help you understand where there are data races. Data races are often really complicated bugs, and to get where they are is difficult. With a nice stack trace, it makes it much easier. And then Heap Sampler is a better way of understanding memory allocations, and generally having it on all the time has also helped a lot. Often these kind of tools are run it, but then your performance is going to be terrible. It's not going to be exactly what's happening. Knowing my job is acting bizarrely, let me quick look at what is happening on the heap sampling, and I don't have to rerun it or risk trying to rerun it and not seeing this effect, has been something that has helped quite a bit. And both tools have helped internally, really, to help us understand Java programs. And I believe I get to my slide questions. So I don't know how fast I was. I can drink water. But more seriously, are there any questions? So the way it works, right, we're ignoring, so TLAB, where basically the idea is all of the interpreter C1 and C2 currently have code that say, I want to allocate. And when they allocate, they say, please TLAB, give me space. And that moment says, well, TLAB, there's no more space. And the way they know that is it has a start pointer and end pointer, and it compares them and says, well, end is going to be further off than my start plus my size. Let me fill it up. And what we do internally is we change that end. Mm-hmm. So we want to, for example, sample at, I don't know, 1,000 bytes after the start of the TLAB, because that's where we're up to in our calculation. We'll just change the end to 1,000, and then we put it back.
Yeah, that's correct.
Okay.
But when you sample, do you sample just the last object or the entire contents?
No, we sample the last object that created that mismatch.
Okay.
Yeah, sorry. I apologize, like I said. Yes. You're gonna want to.
Is that me? Okay, thank you. I have a lot of questions actually, but I will focus on one. So TLABs comes and go, right? So they are not necessarily set allocation failure or something. For example, TLABs can park just because the thread are doing synchronization. So and also some other objects, if it's bigger enough so that you cannot allocate into TLAB.
Yes.
Then that would be go to shared heap.
Yes.
Have you done anything particular for this kind of situation, just to make sure that you cover everything?
So the first case, I don't know that I have handled it, so probably the answer is no, because I'm not aware, so I'll want to talk to you to figure out what I'm missing. The second one, yes, because the second one, the code pretty much says, is it small enough to go into a TLAB allocation? Yes, then I hit it. And no, I still hit it by saying, well, how much do you want to allocate? Is it less than next time I want to sample, or is it more? And at that point, we just reset it. So we handled the outside of TLAB because it's too big.
That's good, yeah.
Yeah.
And also, for the TLAB, I think the whole purpose of TLAB is to make the bumping pointer quick, faster. So
yes.
The allocation is faster and without any race. I don't know what's your details of the implementation. So, I hope, I only hope that you are not going to defeat that purpose by adding more.
No, so the way it works, right, is you change the end pointer, but that you don't do it in generated code. So basically, the whole generated code is exactly the same. We don't touch it. So you have the same kind of, let me go get the start of my TLAB, my top of my TLAB, where I'm up to. Let me get the end, let me do top plus size compared to the end. The only difference of what's happening here is if you turn on start heap sampling, then what will happen is that your end is going to be changed. It won't be the automatic end of the TLAB, it's going to be a different one. So your generated code is the same, runs as fast. However, because you're sampling, you're going to get an overhead of that sampling. And so the smaller your sample rate, the bigger your overhead, but the larger, the less, because you would never really hit it. And so I guess what I'm trying to get to is internally, we set it to 512K, though it's the compiler version of it, not the TLAB version. And the compiler version of it has a 1% to 2% overhead, right? So the theory that we've had, and I haven't had time to do benchmarking since I left on paternity leave, was that TLAB version would have less than that. because we're not even touching the compiled code anymore, right? So we'd be in the 1-2% or even less. But I haven't any proof right now to like tell you, oh yeah, look at these slides, right? Does that answer that?
Oh yeah, please correct me if I'm wrong. It sounds like you make the TLab query fail. Then at that time, then you do the sampling yourself. That's where the sampling happens. Yeah. Okay, great.
So as long as you don't sample as long as you're not sampling, it doesn't change your performance. It's as soon as you start sampling that you will spend time sampling. And that's it.
Go back.
Yeah.
Oh yeah, that's all right. That's a little. Okay. Yeah. Thank you.
Any other?
Okay, let's do one last question.
So I expect that, and I think you were mentioning this, that as people use the ThreadSanitizer, there's lots of bugs that are present, and there are multiple instances of the same bug that will appear in any particular execution. Do you remember one instance and not flag all of them, or how do you reduce the amount of data that you're actually writing out in terms of the races that exist? So for example, in a dynamic execution of the system, which is I think what you're looking at, there's one instance of a race, and then there's another subsequent instance of the same race.
Oh, yes, yes.
Right.
I believe what TSAN does is remember that such a race has occurred and remembers to not bother trying to report that again.
And the other question was, when your application code is using TSAN and apparently you're generating these reports, I would imagine it takes a bit of time before someone fixes an existing race.
Yes.
And how do you deal with flagging new races versus, I mean, do you have anything built behind it to prevent? Well, so the thing is that the signal is where you discover there's a new race. And the noise is where you already know of a race, which you're rediscovering again. And the user of the tool doesn't want to be reminded about races that maybe he's filed a bug and he's going to work on it.
This is a known race, and we don't want to see it right now.
Yeah.
Right, that's the issue. There's an extensive suppression mechanism that you could add entry to that will just force TSAN to not report stuff. And we try not to add to that, but sometimes you have to in the name of expediency.
Okay, thank you.
Okay, thank you.
Thank you very much.
Thank you.